Thank you very much, Sue, and my section, who nominated me to have this honor. As you've heard from her, I also have affiliation with Section 15, Geology. Now, many of you probably are encountering the word taphonomy for the first time. That's fine. By the end of the talk, one of my goals is to leave everybody with a good idea of what taphonomy is. Technically, actually, from the Greek origin, it's the laws of burial. Also, I want to spend some time on human evolution and how those two things relate, and then take you down into the deep time fossil record for a broader perspective of what taphonomy is and what it can do. So I was encouraged to give a little bit of personal history. I was born in Quincy, Illinois, spent a lot of time on a farm with my brothers and my mother that was near there. And on that farm were fossils. These are Paleozoic fossils, and I became fascinated with both the fossil record and with the rocks that contain it. And that took me on a journey through undergraduate school at Washington University in St. Louis, and then I went to Indiana University Field Camp, and I was actually the first female TA for them the second year, and was firmly set on a course as a geologist. But I thought that being an interdisciplinary scientist was actually where I wanted to go, and so I ended up going to graduate school at Harvard University and was taken in as a student by Brian Patterson, who gave me the opportunity to go to the Turkana Basin in Kenya with one of his other graduate students. And that led very quickly to being part of the early wonderful years of Richard Leakey's project in northern Kenya. A great, great opportunity. And I want to also acknowledge Glenn Isaac, who was part of that project as an archaeologist and one of my greatest mentors. So I want you to pay attention to this skull, which was one from the first year of discovery in the Turkana Basin, when there were lots of these kinds of things actually turning up. It was rich hunting. And that skull is all nice and cleaned up, suitable for anthropologists, paleoanthropologists, to get a lot of good anatomical information out of. However, I was fortunate to be there to take this picture of it before it was cleaned of its geological context. And for me, the interest in these specimens was not so much in who they were as species, but in what had happened to them to get them into our hands, the long trajectory of what constitutes taphonomy. And I also want to acknowledge the fact that Mary Leakey was a very wonderful role model as a female scientist at that point. So let's take a closer look at the specimen, which never got a name, a pet name, like some of these early specimens did. It was very much like the Zinjanthropus that came from Olduvai, but it's called 406, and you can see there's sandstone in the orbits. The bone is in very good condition. I had a chance to look at that. So the taphonomic evidence about its history before it became a fossil and afterward as well indicated there was minimum time on the surface for bone weathering. There was minimal transport abrasion, even though it was in a sandstone in a channel, but it did have missing teeth. And we were able to document where it was, where the red star is there, coming out of a sandstone on the edge of this modern channel, and I did the stratigraphy, which here's a couple meters of vertical section, and you can see here that there are some mollusks, lacustrine mollusks up here. There are various strata. The specimen occurred here. It was in a small channel deposit, which in the modern lake margin of the northern Turkana Basin would have looked very much like this. So the value to me was to put this hominid specimen in its place and understand how it represented the population of that time. And all these indicators suggest that it lived and died not very far from where it was buried. Okay, so then this is a kind of taphonomic visual paradigm, and it combines ecology and geology. If you start in the biosphere, things die, there are filters represented here, organic remains, delayed burial, recycling, immediate burial, lots of ways to get into the buried environment, and then geological processes take over. And eventually, if there's preservation rather than destruction, you end up with fossils, and then this part is not really taphonomy, it's just showing, going back to what you want to know about the original biosphere. Now, taphonomy is really interdisciplinary. And although it's not always called taphonomy, we have forensics and conservation biology intersecting with what we're finding, and a lot more that I won't go through in detail. And even astrobiology now is interested in this biosphere to lithosphere transformation, because if there was a biosphere on Mars, there would be some transitional things that had happened in order for that to be preserved for billions of years. So what taphonomy has now become is the tests of live dead fidelity. How well do the dead, buried, and fossilized actually represent what was living once, long ago? And this makes it directly relevant to ecological recycling processes. I've had to learn a lot about ecology myself, and then the geological depositional processes, and diagenesis as well, which is basically turning the stone in the popular language. So now let's take a look at the hominid fossil record. Very wonderful reconstruction of some of the players up here by John Gurche, and you can see this array. There are 3,000 more specimens now as of 2019, more coming in. This is an exciting area of science for sure. Most of this earlier or all of it is in Africa, and when you get up into our own genus, that's when our ancestors began to get out. And also, there's an archaeological record, of course, and the yellow stars show some of the major transitions with the earliest known artifacts down here, older than 3 million now, so long before our own genus appeared. So there's something important to see in this as well, which is that these bars indicate dating error and unknown ranges. These are called range charts. Of course, geologists think in terms of time going down, older and younger. And so these are sometimes large amounts of error, although you know that these specimens did occur in these time slots. But they're what's called first appearances and last appearances. Extinctions are not very well defined in a lot of cases. So one of the big questions in human evolution for a long time, going back even to Darwin, is environment, climate as a driver of human evolution. And some of this then on the right side is represented in astronomical cycles, which are recorded in drill cores, and other ways, ice cores for the more near time framework. But we have tremendous amount of data about how environments have changed during this time slice, and notice that this is a time slice from 3.3 to 2.6, so just part of it with some of the major archaeological events happening there too. And so just some of these species that are represented here, how do they relate? Do their appearances, disappearances correlate with anything going on with the climate? Well, there now has been a wonderful drilling program in the lakes, which is the Hominin Sites Paleo Lakes drilling program, and the results are coming out. This was started in 2012. And so these records indicate different things that are going on with the climate and the grasslands and various other wiggles in the trajectories through time. But the problem with this is that these errors, the errors are too great in most cases to say how the climate changes are relating. Now you can model it, you can take averages over sometimes and then fit them into the errors on these fossil records. But it's a continuing issue, and this is just representing it in a more simplified form so that you have these species, the living ones that existed in this model, and then the only ones that we know about are here. So there's missing species and an incorrect record of the first appearance. And the causes can be just simply lack of strata or taphonomic biases of various scales. So now I'm going to transition and take you down through the deep time record briefly. This is a user-friendly depiction of it, not really with these intervals to scale. But the same problems that apply to the hominin record apply to all of the fossil record. I've been fortunate to work in a number of different field areas. These are just a few of the photographs. But looking at taphonomy back and the context of fossils and their preservation state back almost 300 million years during the course of my career. And I've also had a wonderful opportunity to study modern processes of bone preservation and destruction in Amboseli National Park in Kenya for about 44 years. But my focus has been on the preservation of vertebrates and terrestrial environments. I've also worked some on plant remains, but a lot of other people have been working on the marine record as well. So I want to just quickly try to get through an examination of incompleteness. Darwin understood this and characterized it in this wonderful metaphor of the book, Missing the Pages. He probably didn't think about what we call now taphonomy. It was more the missing parts of the stratigraphic record. And some people have assumed that the lines, the pages, the chapters, there's a kind of randomness in what's missing and what isn't. But in fact, as a thought experiment, what would a complete fossil record look like? I've divided this into producers and consumers, which in this diagram are just 30%. And it could be any interval of geologic time. And then this consumers, then because they often have hard parts, or they're more durable, they get preserved better than the producers. And then there's a lot of geological incompleteness because of missing strata, which actually increases as you go back farther in time. Notice there's been a switch to 60% consumers. So in terms of numbers of what's missing, that's been estimated to 98%. And this is from one quote. Now probably more than 99% of the species that ever lived we'll never know anything about. Not a great testimonial to the fossil record. And then if you look at it in terms of biomass, there's this 83% are the producers. You can see the corners with the viruses. And in the paleobiology database, it's 92% of these are the animals, and only 7.8% are the primary producers. Now this makes sense because life is designed to feed on itself, to convert the living and the dead back into the living. And how did early post-mortem nutrient recycling affect the fossil record has been a question that I've been really working on in the last several years. if you think about it, efficient recycling means no fossils. So the fossil record, it turns out, is also the inverse of ecological processes. And that means that paleontology and ecology are two sides of the same coin. We study what didn't get recycled in the original ecosystem. This is a famous curve by Jack Zukowski, a record of biodiversity through time. It's often assumed to be a representation of a lot of the rest of what happened to life. It may be. However, as I showed you, it represents just a small corner. And in fact, as he said, 1,000 of the families, this is based on families, of marine, shelly, and vertebrates are missing. And so it is one record of biodiversity through time, but how it actually represents life through time on Earth is open to, I think, more question. So this is, then to finish off, I've created these simple models about nutrient recycling. This one, with the soft-bodied organisms, you can imagine the beginning of life on Earth. Everything was fairly soft-bodied to begin with, just basically organic molecules. And then cell walls were created, and then more structural support, mechanisms for predation, defense, and we got what I love this word is recalcitrant organisms, or parts of them. And when you get those, then you start getting a fossil record. And the dashed line is, there's always some special circumstances that can preserve unusual fossils. But in general, the fossil record is controlled by this. And then the slow nutrient release these recalcitrant organisms would slow down the nutrient release. But then most of it would probably be still going like that. Well, you can imagine that it could sometimes be like this in some places and some time periods, which would change what's going on and increase the fossil record. Okay, so this creates a new agenda, I think, for thinking about the fossil record. How do changes in the durable parts affect ecosystem energetics? And this also works on other planets, potentially. Questions, and I'll go through these really quickly, but this raises a lot of new questions. How does speciation, diversification, and extinction of the preserved compare with those of the easily recycled? Are we basing understanding of evolutionary history on fossil organisms adapted to ecosystems with less efficient or slower nutrient recycling? And what special conditions led to the large amounts of storage of unrecycled organics, such as our coal and hydrocarbon reserves? And here we have a wonderful cartoon from the New Yorker, and I modified it a little bit because humans are doing their darndest to stop natural recycling of all kinds of materials. This gets into material science. The consequences for decomposers. And, of course, we're creating a huge potential fossil record of our own. So back to this, pre-human nutrient recycling, what might have been called normal. And now, not only are we slowing the nutrient recycling here, but we're also adding a whole lot of newly unearthed energy and nutrients from the fossil record. So I'll leave you with every fossil was once connected to an ecosystem that supported in life. So although it's not a huge record, it's a tiny record, we can use what we know about ecology and taphonomy to expand what each fossil can tell us. And think about this preservation question. And I'm advocating for a much more interdisciplinary approach to the question so that we can really understand what happened to life through time. Thank you.